Sorry.
Bad ideas.
Yeah, AK, why don't you just take it, man?
Yeah, AK. Come on.
So if you have nitrobenzene, if we wanted to reduce that to, we learned these 5 reductions. If we want to reduce this to aniline, how would we do that? H2
PD.
palladium on carbon. Right? That's one way to do it. There's actually another way to do it. Right? There's actually another way to do it. You could also use zinc and HCl. That's one of the ways sapling does it. It uses zinc and HCl. So that's another way. If you see zinc HCl, that can also reduce the nitrobenzene to aniline. Okay? Another one that I didn't give you maybe the whole picture for. If we want to take toluene and turn it into benzoic acid, what kind of reagents will we use for that? Chromium is one type of reagent we could use. Any type of chromium, so chromium oxide, CrO3, H2CrO4. Chromium, anything with chromium would work. That's one option. Or the KMnO4, the permanganate. Either one is an option. Chromium or permanganate. Either one works. If you don't have to have them both, there's either one. Okay? But there's one actually last step you need to do for a workup. So this is a carboxylic acid. Is this soluble in an organic solvent right now? Is it charged?
Yeah.
So like dissolves like. What is this going to be soluble? Is it going to be soluble in an organic solvent? Organic solvents have carbon. This has carbon. Is it going to be soluble in an organic solvent?
Yes.
There we go. Okay. But originally, right, it was actually, there's an intermediate that we failed to mention. At first, it's like this. It's a carboxylase. There's an O minus. So what do I need to add to go from here to here? That's O minus. So bases are electron rich or electron poor? Bases are electron rich. So to go from here to here, I need to add. So something like H3O plus. So in sapling, one of the final steps to go, a lot of times they'll say from chromium or KMnO4, you need another step with acid, because this is actually the thing you form, and then you need acid to turn into the non-charged species, right? And why do we need to do that? Because this would be soluble in water. If we're in our step funnel, right, where do we want our, can we rotovap water? No, we want to get all the organic stuff in the organic layer, right? So we got to protonate it, use an acid to get to the carboxylic acid. So they use it as a, I don't include it usually because unless we're running this reaction in lab, sometimes I think we get too worried about these little minutia details. Like, it's okay. Right? You get the idea. Yeah.
So what would KMnO4 do to like a longer carbon chain?
It'll just chew it all up. So it still chews it up, right? It still does the same process.
So it gets the same product even?
All the same product, right? It doesn't matter if I had a longer chain here, I would still chew that all up and just get the one carbon left over. And those carbons would be oxidized as well to different carboxylic acids, essentially. Cool. Good? So those two like kind of just little differences, and I want to make sure we have those good. Otherwise, okay. So now I want to take your class notes out. Take your class notes out from, I guess it'd be Wednesday. And we're going to look at, so we've done what have we done a lot of? We've drawn a lot of resonance structures of the starting materials. Right? But now what I want you to do, right? Now be careful. So let's say I have, and what is this guy called?
No.
Anisole. So I have anisole. And the question is, right, we've done some resonance structures, and what have we shown with resonance structures? We've shown that anisole, this substituent is an activator or a deactivator? An activator. All activators direct electrophiles to go where? Para and ortho, right? And we found that out by doing resonance structures. Right, so that, hopefully that's been proven in your mind. We did that on Wednesday. But now I want to show you, so that was kind of like the chicken. And now we're going to say, well, let's look at the egg and see if that also proves that we should go ortho and para. Is that making any sense? The egg. What came first, the chicken or the egg? Yeah, see? All right, so we looked at the chicken, we looked at the resonance structures, but now let's say, okay, what if we actually do the reaction and make the sigma complexes? Are we going to find the magical fourth sigma complex? It's magic. Well, it's not really magic. You always have 3, but if you can have 4, is 4 more than 3? Yes, philosophically, well, maybe today. Who knows, right? But so what I want you to do, if you look at your class notes, we need to go through, and I want you to say, okay, prove it to yourself. I want you to add the electrophile ortho, add it meta, and add it para, and then draw the sigma complexes for each, right? So that's at least 9 sigma complexes, and see if you can find one that gives you if one or more than one gives you the fourth sigma complex. And if you can make the fourth sigma complex, what does that tell you about putting the electrophile there? Good or bad? It's good, right? So let's do that. Let's say, add it ortho. That's a sigma. Add it ortho. Right? And let's just we'll just go back to old E plus. Add it meta. E plus. Add it para. E plus. So I want this half of the room to do this. The other half of the room is going to do this one. On the back side, you have this molecule.
It's so small, I can't see it.
What's this molecule called? Benzaldehyde. And so I want you to draw the electrophile adding here, ortho. Have it add meta. And have it add para. And that's for this half of the room. All right, so Marty over. You guys are doing this one. Everybody else over there, you're doing that one. Ready, go.